Now for this final part of the problem, we are going to find for when, let's see here, when z is much less than a, right? So if we come back to our drawing up here, let me just go ahead and bring this down. So now when we have this will end up being, I wonder if I could shrink it actually. So we can, we have some point z right here, and then if we just like shrink it down all the way down to it's essentially just a little dot, but we keep that distance z above it. The more we shrink this down, the more this is going to look like, further and further away. And if we shrink it down small enough, this will end up being 0, right? It makes sense, but we want an actual value for this. So anytime that we're going to have, you have something that's close to 0, but not quite, that should scream Taylor expansion, right? Taylor expansion and Taylor approximation right there. So we'll go ahead and do that with the electric field that we previously had. So we'll go ahead and scroll up. This is the electric field that we previously solved for. So we're going to evaluate this electric field when z becomes, or whenever we get to a value that's close to 0, but not quite. And just to verify, if we go ahead and say that, this isn't part of the problem necessarily, but just to verify that this whole thing does in fact go to 0 whenever this becomes infinitely small, what we have is this whole factor right here will end up becoming, well, this will become 0 because a is much smaller than z, so this whole thing will become 0. Tangent inverse of 1 ends up being pi over 4, right? Pi over 4 times 4 over pi equals 1. 1 minus 1 equals 0, so this whole thing goes to 0, so that makes sense. But we want something that's close to 0, but not quite it. So we're going to go ahead and, so this is our problem child right here, so we're going to go ahead and Taylor expand that. And the way that you Taylor expand something, just as a refresher, it has the general form of you have some sort of function, and then to do the Taylor approximation of it, you just evaluate that function at 0, which we kind of just did, times that derivative evaluated, the derivative of that function evaluated at 0 times x, and then x over 2 times the double derivative of that function evaluated at 0. I'm just going to go ahead and move this out of the way. So one of the ways that we can go ahead and do that is, use a calculator, of course. So we'll go ahead and, so we already know this is equal to 0, right? So I'll just go ahead and put that down here, just call that 0. Actually, I'm sorry, no, it's not equal to 0. It's just like we said, so it's just this tangent inverse here evaluated at equal to 0. So this function right here evaluated at x equals 0 or a equals 0 is equal to what we said before was pi over 4, right? And then the next thing is us trying to figure out what the derivative of this function here. And, I'll go ahead and plug that into the calculator. Let me get a little more room down here. So this derivative, whenever you plug it into the calculator and start working on it, is equal to a over 2z squared, a times the square root of all this stuff right here, a 2z squared plus 1. I'll go ahead and zoom in, give us a little bit better room. And then that whole thing, this denominator keeps going out, times everything that's inside it, a squared over 2z squared plus z in this sense. So we'll go ahead and take that and go ahead and evaluate it at, x equals 0, but for us this is actually a, so a equals 0. So this will be 0. This whole thing goes to 0. This a goes to 0, right? Ends up being, of course, anything with a numerator of 0 ends up being 0. So this whole factor here ends up going to 0. And the next thing to do is to take the double derivative of that and of this function right here and evaluate it at f equals 0, and we'll do that now. We'll probably need some more room, so I'll go ahead and just bump that down here. Evaluating this at double derivative of f equals 0, so again, plugging this into our handy dandy calculator, Wolfram, we have this. And this may seem, kind of scary and complicated, but ends up, collapsing down pretty nicely whenever we evaluate it at a equals 0, because a is our variable value here. Okay, so now evaluating at a equals 0, so all these a's turn to zeros. This goes to 0, 0, 0. This is 0. So here you have 2 times, z squared over z squared, so that ends up just being 2. Let's go ahead and simplify that. I'll move this down 1. So we have, let's see here, 2 over the square root of 2 times 4z to the 4th over z squared, square root of 2 to the 3rd, then 16 z to the 4th. Let's do some canceling out. There we go. This will turn into, let's see here, oops, let me change that. These 2 square roots, 4 goes away. This turns into a 4. Actually, square root, sorry. This ends up square root of 2 times, square root of 2, oh my god, square root of 2 to the 3rd is actually equal to 2 times the square root of 2, so we can actually just cross out all of that. So that 2 goes with it, this goes with it. Let's see here, we can cancel all these z to the 4th, and all that's left is 1 over 4z squared. All right, so that is our next term that we can put right here, and then since x is actually our a is our variable, so we have a for 2. So we'll go ahead and put that right here, so it'd be a squared over 2 times 1/4 z squared. So this is our Taylor approximation for this right here. So we'll go ahead and zoom back out and plug that into our equation. Now we'll throw everything in. Ends up being pi over 4 plus 8 z squared once we get everything done. Okay. And then now we'll go ahead and just do some canceling out right here. We'll go ahead and just distribute this into here. So we'll have a 1 and then 4 pi times all this stuff right here. Let me go ahead and do that real quick. Pi over 8 z squared minus 1. This is all a z hat, by the way. Sorry, that was a z hat. Didn't mean to freak anybody out. These cancel out. Almost done to the end of the page. And so we have sigma over 2 epsilon naught. We have an a squared 2 pi z squared. That's still a z hat component. What we can do is recognize that sigma is actually equal to the charge distributed over the area, and our area is actually equal to a squared. So moving that back over here, making that substitution, getting into a more familiar form, we have 1 over 4 pi epsilon naught q over z squared in the z hat direction. And that's exactly what we're looking for as we So we had that square patch, and we zoomed out further and further and further. Although this would, the electric field will eventually go to zero, ends up looking like eventually just a point charge, which is exactly what we ended up finding out here.